Alrighty, this time we're going to look at some abnormal EKGs. Last time we went over kind of the normal timing and flow of the electrical signal through the heart. We looked at more or less a normal EKG from lead 2, which looks something like this. No times or anything on it, but that's your P wave, Q, R, and S complex in the T wave. Now, what you're going to have to do, and I think I mentioned last time, if I give you a normal EKG tracing, you could label the curves or the waves, P wave, QRS complex, you can call it the QRS complex, and the T wave, and tell me what they correspond to, what they're measuring electrically, and what they relate to mechanically, what they're associated with mechanically. That's what you have to know. Now, what we look at now are some arrhythmias or dysrhythmias. Anything that interferes with the conducting pathway or the timing of these electrical events has the potential to affect the heart's cardiac output, its pumping ability. Now, that being said, I'm going to go through these. You're not going to have to interpret abnormal EKGs. One reason, this instructor probably can't really do it. I'm going to make up a little stuff. I can look at it in general, but honestly, to interpret EKGs, cardiologists go to a lot of school. They can do it. You can't learn it in an hour. I can't teach you it either, or 15 minutes, or whatever we got here. So I've got some extra pieces of paper here. I may give you some tracings of sort of in general what an EKG might look like or how it's affected. It may not be all that accurate, and you're not going to have to identify or interpret abnormal EKGs. What you will have to do is kind of give me a text description of the arrhythmia. And I'll give you a definition of them, and then I might show you what a few of them look like. If I remember, I'll post a little sheet on Blackboard with the names of the arrhythmias, and you just need to define them. So you're not going to interpret the EKGs, don't worry much about that. If I can, I've got a nice video that goes along with this. It shows you the heart beating, it shows you an EKG, and they induce all these arrhythmias. If I can get it uploaded, I'll give that a try. I'll post it if I can get it. All right, so normal EKG we've got. Now, some of the abnormalities, they've got names. One of them is, if we can get it on here, a bradycardia. A bradycardia is an abnormally slow heart rate. Generally, it's going to be a resting heart rate. Less than 60 beats per minute. Now, anytime you have any of these abnormalities or arrhythmias, you have to kind of look at what it's doing to the heart, because sort of the average Joe, couch potato like me, if I have a resting heart rate under 60, there might be something wrong. Something maybe happened to the pacemaker, and then the next fastest cell took over, my heart's at a slower rate. It's possible. On the other hand, if you measure the resting heart rate of any well-trained aerobic athlete, like someone that does cross-country competitively or something like that, they will have a bradycardia. Because remember, cardiac output is determined by heart rate and stroke volume. And stroke volume is how much blood is ejected per beat. A well-trained aerobic athlete, their heart is a little bigger, their pericardium is bigger, their stroke volume is bigger, so they can pump the same amount of blood as I can at a lower rate, because each time the heart beats, it ejects more blood. So it kind of depends on the cause of the bradycardia. In an athlete, it's not of any clinical significance, but in a couch potato, it could be. All right, so that's a bradycardia. The EKG will look relatively normal, P wave, QRS complex, T wave, but if you look at the EKG, of course, the rate, and as I mentioned, I think earlier, T wave, P wave, Q, R, S wave. The time between beats, so from the R wave to the R wave, say, that's the seconds per beat. In a bradycardia, the whole EKG will just be spread out. This distance, or time, would be larger. So the whole EKG is normal, just spreads out. Another arrhythmia is called a tachycardia. In a tachycardia, the resting heart rate is over 100 beats per minute. Now, tachycardias can be caused by numerous things. You could have a sinus tachycardia, they call it, sinus from the SA node. If the SA node is firing impulses at more than 100 times per second, then your heart rate will be more than 100 times per second. So you can have a sinus tachycardia. It just means the SA node's firing too fast. You can also get a tachycardia that's caused by what they often call ectopic focus, I think is the term. Imagine, here's your heart. I'll do the best I can here. Look more like the prostate gland, but that's the heart. You normally have your SA node acting as the pacemaker. What would happen if some other cell, ectopic just means kind of in the wrong place, let's say a cell over here in the atria, if that cell for some reason started generating action potentials faster than the SA node, it's now the pacemaker, the heart rate will go up. That's tachycardia due to an ectopic focus or a cell just taking over the pacing at a higher rate. The EKG for tachycardia may look normal. If it's due to the SA node firing too quickly, everything will be normal, but again, this time interval between the beats will get compressed. Now the problem with the tachycardia, most of the compression, if you will, if you speed it up, you can make the whole EKG, the electrical signal, move a little faster. This will get a little squeezed together, but mostly this period right here, that's diastole. That's when the heart's doing nothing. What about people? Well, that's not important. Well, what's happening during diastole? That's filling. So if you start getting a very rapid heart rate, what really gets shrunk down, gets reduced in time, is this filling period. Sort of diastole gets shorter. You can get insufficient blood flowing into the heart. That's going to affect stroke volume, so cardiac output can go down if heart rate gets too high. Not enough filling time. That's a tachycardia. Let's do a couple more while I have room. How about heart block? All right, there are several different types of what they call heart block. Different degrees. There's a first degree, second degree, third degree AV block or heart block. And they all have one thing in common. Remember, when we're looking at the heart, SA node is here, AV node is here, then the AV bundle it goes down. In heart block, something is interfering with the conduction between the atrium and ventricles. Imagine it's usually the little, they call them nodal fibers, coming from the AV node into the AV bundle. There's some smaller fibers kind of penetrating that connective tissue disc. Those often have something wrong with them. So the conduction is blocked between the atrium and the ventricle. Let's look at the most extreme case first, because it's actually easier to explain. Imagine if you came in here with some kind of cauterizing tool and you just cut this connection right here. Well, what's going to happen now? Of course, the SA node is still going to fire, the impulse will sweep through the atria, but now there's no electrical connection between the atrium and the ventricles. So what are the ventricles going to do? They're going to stop? No. Remember, many cells in the heart can generate their own action potential, but typically the ones in the ventricle are at a much slower rate. So you might have the SA node firing 70 times per minute, some other cell taking over the pacemaker role in the ventricles, and it may only be at 30 or 40 beats per minute. Let's see if I can scribble kind of what it might look like here. You get a P wave, a P wave, a P wave, then you might get some random QRS complex, and a T wave, P wave, P wave. So you get lots of P waves, because they beat a faster rate, and then QRS complex is kind of scattered out. There's no more electrical connection between the two sets of chambers, the atrium and ventricles, so they're kind of working independently. Again, a ventricular rate drops low enough, like around 40 or less. That's barely enough to keep you conscious. That's going to have to be repaired. That's complete heart block. The other extreme, the less detrimental heart block, is first degree heart block. You could have this one and you might not even know you have it unless you have an EKG done. In first degree heart block, I'll exaggerate it a bit. Here's your P wave, QRS complex. Remember before on a normal EKG, we looked at the P-R interval. P-R interval. That's a period of time from when the SA node fires until the impulse makes its way to the ventricles. Normally, that PR interval is about 0.5 0.16 seconds. Again, that's a period of time it takes for the impulse to go through the atria and then get delayed for a tenth of a second in the AB node. It's about 0.16 seconds. If this time is prolonged, that is, if the PR interval is greater than, I believe the value was 0.20 seconds, if it takes more than 20 hundredths of a second for the impulse to go from the SA node into the ventricles, that's first degree heart block. The EKG may look relatively normal except a long or prolonged PR interval. That's first degree heart block. Second degree heart block, as you might guess, is kind of between these two. What happens in second degree heart block? You may get, scribble it on here, you may get a P wave, a QRS complex, and a T wave, a P wave, QRS complex, and a T wave. Then you might get a P wave, then nothing. Then a P wave, QRS complex, and so on. So what happens is you might get several normal beats, but then you drop a QRS complex. That means, an impulse goes from the atria to the ventricles, everything's fine. Impulse goes from the atria to the ventricles, and everything's fine. Impulse goes from the atria, and it doesn't make it to the ventricles. Maybe every third beat, you might drop off a QRS complex. That is second degree heart block. So those are heart block. They're all interference in a conduction between the atria and the ventricles. There, new sheet of paper. All right, let's look at a couple more if I can squeeze them in here. P, B, C, and a P, A, C. These are similar. PAC is premature atrial contraction. PVC is premature ventricular contraction. They're caused basically by the same thing, it just depends on where they're located. Let me draw myself another little heart here. Atria, ventricles, there, lovely. Like I said, those years of art school have paid off. Normally, the SA node is a pacemaker. So it fires, the impulse groups to the heart, everything's fine, and you get a normal EKG. But what happens if some cell over here, again, it's referred to as an ectopic focus, the SA node fires, SA node fires, SA node fires, everything's fine, but then, kind of from out of nowhere, some other cell in the atria just generates an action potential prematurely before the SA node fires. You might see something like this. P wave, QRS complex, T wave. P wave, QRS complex, T wave. Then really quickly, another P wave, QRS complex, and a T wave. So notice the time between beats here and here, that's normal. This one is too early. It came too fast, hence the premature part of premature atrial contraction. But the impulse still originated in the atria, so the EKG might look relatively normal. It kind of depends on where the ectopic cell is. If it's very close to the SA node, P wave might look fairly normal. If it's way over here on the other side, you might notice this P wave gets a little abnormal, maybe inverted or have a different shape to it. That's premature atrial contraction. PVCs are basically the same thing. PVCs are premature ventricular contraction. It's the same setup, except the ectopic cell, let me get my eraser. The ectopic cell is not in the atrium. It's somewhere in the ventricle. Of all arrhythmias, this one's actually pretty easy to spot, even with minimal training. With this one, the SA node will fire normally, and you'd have a normal EKG, but then, at some point, you get this ectopic cell in the ventricles generating action potential prematurely. So what you might get is a normal beat, P wave, Q, R, S wave, and a T wave, but then some cell over here in the ventricles just spontaneously generates an action potential before the SA node fires, and what you'll get is you get a premature beat. There'll be no P wave, because the impulse cannot be conducted from the ventricles back up into the atria. It doesn't work that way. It's kind of one-way flow. So you get no P wave. Also, as I tried to indicate in my little pathetic drawing here, the QRS complex will look odd, wide and bizarre. It often takes longer, because rather than going down the middle of the septum and then apex to the base, it's kind of going from one side all the way over here. Also, the pen deflections of the QRS complex may look different. Because remember, normally the impulse is going down the interventricular septum to the apex, then it moves up from the apex towards the base. If the ectopic cell is here, the direction of travel for the impulse is kind of the opposite. It's going to be going from the base to the apex here, and then it's going to go up the interventricular septum. That makes the QRS complex look odd. Now, these, I'd like to think I'm responsible for many of these. PVCs, depending on how many you have, it probably vary depending on who your cardiologist is, but if you get more than like 3 a minute or 6 a minute, then they might be of clinical significance. Small numbers, just every once in a while, getting a PVC or PAC, they're not considered to have that much clinical significance, and they're very common in college-age students because this ectopic cell can fire due to things like stress, lack of sleep, stress is my part, stimulants, caffeine, nicotine, that sort of thing, can overexcite some of these cells, will generate action potential. So it's actually common in college-age students. If you just have a few, it's no big deal. Now, if you get a lot of them, they'll go in, I guess, for further evaluation because they can also be caused by lack of oxygen to the cells, which could indicate some blockage of the coronary arteries or something. Also, something to note: the next beat after the PVC is often, it feels like it's delayed a bit. This is sometimes referred to as a compensatory pause because that first beat, you got a longer refractory period. It almost feels like your heart skips a beat. You know, it goes thump, 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 and then there's another beat, kind of an extra delay there. It takes longer for the heart to sort of reset electrically. So those are PVCs, PACs, premature atrial contractions, premature ventricular contractions. There's a couple others, I'll run through them quickly. Atrial flutter and ventricular tachycardia. Atrial flutter is just very rapid impulses in the atria. Basically what happens is the atria gets distended, they get too big, or you get damage in the atria. And normally what happens is the impulse goes through the atria. You can imagine the atria is kind of if you took a cross section of it, you can imagine it's kind of like a circle, like that. SA node is here somewhere. Normally as the impulse travels away from the SA node, it takes it a little while to get back to kind of its site of origin, let's say the SA node. Normally these heart cells have a relatively long refractory period. Remember, refractory period is a period of time for excitable cells where even if you stimulate them, they will not generate another action potential. They're not sensitive. So normally this impulse travels around. When it gets back to its sort of site of origin, this cell is already in its refractory period, so it can't be stimulated again. The impulse stops, and then it generates another one. Well, imagine what would happen if your atria just got bigger. I'm going to overwrite all my junk. Now the impulse is going to go the same way around the atria, but because it's got a longer distance to go, by the time it reaches the point of origin, if these cells are out of the refractory period, the same impulse just re-enters and kind of goes around and around and around. It's sort of a circus movement there. And the rate is incredibly high. Basically, the atria is sitting there vibrating. They're not pumping anything. Now again, it's the atria. That wouldn't kill you. I think George Bush Sr. had an atrial flutter, they call it, at one point. I think his symptoms were a little short of breath. So again, the ventricles are the main pump, but when the atria are in flutter, they're going so fast they're not pumping anything. But again, your ventricles are the main pump. The same thing in the ventricle. It's not called ventricular flutter. I believe it's called ventricular tachycardia. That one's much more serious. If you get ventricular rates over 250 per minute, again, it can be caused by the same thing. Enlarged chambers, damage, makes the impulse move around the old scar tissue. That takes longer as well. But in ventricular tachycardia, the ventricles are going too fast. They're not having enough time to fill. Cardiac output drops tremendously. That can be lethal in and of itself. Last thing I'll just mention, the last one is fibrillation. You can have atrial ventricular fibrillation. I'll talk about ventricular fibrillation. It's the bad one. In fibrillation, it's a little hard to explain. Fibrillation is complete lack of electrical coordination in the heart. There's a flow sheet. So if you imagine this is your ventricle here, I'll just kind of draw it like a big U-shaped thing. Normally, the impulse travels through a pathway, a constant pathway, goes the same way every time. But if something disrupts that and the impulse sort of splits, one thing that can cause that is heart damage. You know, imagine you've had a mild heart attack and you have a mass of dead tissue here. Now, if it's minor, you'll recover. The damaged cells will be replaced by scar tissue, connective tissue, because cardiac muscle cells don't regenerate much. So let's say you've developed a few of these patches of scar tissue in your heart because of damage, mild heart attack, something like that. One of the things that can happen when the impulse reaches a patch of this scar tissue won't conduct nerve impulses. It's mostly extracellular matrix. So the impulse basically splits and goes around the damaged patch. Then it reaches another one, it'll split again. Then it'll reach another one, split again. And what happens is, eventually, where you had one pathway of this action potential moving through the heart, now it's split, and they're going every which way. So what happens, the heart just kind of sits there and sort of quivers. Some cells are contracting, some are relaxing, some are in refractory periods, some are out of the refractory period, ready to contract. They've lost their coordination, so it kind of sits there and quivers. It pumps nothing. So they can be caused by damaged tissue. They can also be caused by an electrical shock by alternating current, like the wall current in your house. That oscillates, I think what, changes polarity 60 times a second. I think we're using 60 hertz power here. If you apply that to the heart, it also scrambles it electrically and the signal gets all messed up, and that will cause fibrillation. This is what they always show on TV, where this person sort of flatlines. Fibrillation, once the heart starts fibrillation, it's not going to come out of it on its own. It has to be some outside intervention, and they call it defibrillation, which is basically they take two big electrodes, put them on the chest, and they pass several thousand volts through the heart. The idea is you depolarize everything, all the cells are in a refractory period, then hopefully a normal rhythm will take over. All right, that's about all I'm going to do with the arrhythmias. I'll try and post just a little sheet with the names of the arrhythmias, and like I said, you just need to define them. You know, tachycardia, faster than normal heart rate, resting heart rate over 100. Bradycardia, resting heart rate over 60. Heart block, interference between conduction between the atria and the ventricles. So define them in terms and words. You're not going to have to interpret the EKGs, and I'll try and remember to put that list up. Take care.